me for a second. It was so easy to really out there in class, and like 2 hours. Right. And then she didn't say anything when we showed up. Yeah.
All right, how's everyone feeling today?
Yeah.
Glad to hear. Also glad to hear. Just 1 sec, my computer's being weird. Any questions, needs, concerns, etc. before we get started today? All right. This is a sign that had too many tabs open for too long. All right, well, while I'm waiting on my computer to wake up, so, last time we looked at Newton's third law of motion, describing how in an interaction between two objects, one will exert force on the other must exert the exact same amount back. Every single force in the universe is part of one of these third law pairs. We then began defining momentum, and today we are now going to take momentum and compare it back to what we've just been discussing about the laws of motion. Very primarily laws, I'd say, 2 and 3. Any minute. It's always a great way to start the day when machines don't do what you ask them to. I personally feel that the machine uprising is already here, but since desktops and laptops aren't capable of really threatening us, all they do is just act super passive aggressively. So if your toaster's acting up, be nice to it. All right, let's see. Just gonna go without my notes for a minute. Definition for momentum that we discussed last time is momentum is a measurement, a vector measurement of how hard a moving object is to stop. The formula reads as such. Momentum, seen here as the variable rho. Rho equals mass times velocity. So the more mass something has, the more difficult it is to stop while it is moving. Again, you wouldn't really want to jump out in front of a moving vehicle at any speed, if I'm being honest. And secondly, mass is times velocity. So the faster something is moving, again, the more difficult it will be to bring to a complete stop. you've ever driven a fast car, you know that it's usually a bad idea to just slam on the brakes and expect to stop very quickly. And definitely if you're driving a truck, it's a bad idea to slam on the brakes and assume you will stop quickly. Because if you're moving very fast and have a lot of mass, you will have even more momentum and be even more difficult to stop. We looked at various scenarios involving momentum. And furthermore, we described the difference between momentum and impulse. No, sorry, that's the wrong word that starts with I. Momentum and inertia, excuse me. Inertia is, as discussed in Newton's law, the first. Inertia is an object's tendency to innately keep doing whatever it is it's doing, even if that is staying still. Whereas momentum is a measurement of how hard it is to stop a moving object, and therefore you have to be moving in order to have momentum. So that's the key difference between the two concepts. Inertia tells you to keep doing whatever you're doing, even if that means remain in place. Whereas momentum only has power if something is moving. Is that difference clear before we move on? Okay. Now, as we kind of hinted at I'm getting my sections mixed up. Momentum is kind of weird in that it's something that an object can possess, although it's kind of hard to view it directly. There are a few things that we know of in the universe. Again, know is a strong word because physics is always just our best, most educated guess. Momentum is one of those things that's kind of hard to pin down because you can't really ever see it directly, right? If I told you I'm holding 5 meters per second of momentum in my hand, would you believe me? Sorry, 5 kilogram meters per second of momentum in my hand. Would you believe me? Would you be able to see that? No, momentum is kind of weird in that you can't observe it directly. All we can do is observe it indirectly if we observe an object moving. So the momentum itself is kind of this invisible thing that just compels matter to keep moving forward. And one of the very weird things about momentum is that momentum levels can change, and the momentum itself is able to switch between objects that can possess it. Momentum is this invisible thing that matter can possess that compels it keep moving at the same speed in the same direction. And that invisible, intangible thing can be taken from an object and given to a different one. The primary method by which something's momentum is is changed in any way, shape, or form is through something called an impulse. This is a new vocab word. Does it make sense that an object's momentum level can change? Okay, mostly like nodding, good to see. And looking at the formula for momentum, I hope it should make sense that momentum levels can change, given that an object's current velocity is capable of changing. We've looked at accelerations, we've looked at situations where a velocity changes. So, very straightforward, if velocity changes, your momentum must be changing. Momentum is how hard you are currently to stop, but that can change if you speed up or slow down. So momentum can change, and the mechanism through which that occurs is called an impulse. This is just the fancy physics way of saying change in momentum. Impulse is defined as the change in momentum. It's just the verb for the act of your momentum changing. So any change in momentum at all we call an impulse, kind of like how any change in velocity is called an acceleration. Very similar kind of vocab difference there. Impulses occur when an object's velocity due to a force causing it to accelerate frankly, it's very similar to acceleration because acceleration causes impulse and vice versa. If an impulse is a change in momentum and momentum changes because velocity is changing, velocity changing is an acceleration, therefore impulse causes acceleration, and therefore technically acceleration causes impulse. Oh, I promise that will make sense. So impulse is just a new vocab word. It's just describing the change in an object's current momentum level. And because physicists need to have a variable for everything, they decided to give impulse its own mathematical variable. However, they couldn't choose one that made any sense because the letter I is already spoken for. So instead they gave it the letter J. Because of course. So if you see a lowercase j in any formula, that is referring to impulse. If it helps, you can call it gympulse. Gympulse and momentum. It's kind of, I find it kind of amusing that both variables related to momentum, either momentum itself or impulse, have letters that don't really make sense when spoken aloud. But that J on screen right now is the symbol for impulse. And the base definition of impulse is just change in momentum. So this right here, delta rho, is the change in momentum. If you gain 10 kilogram meters per second of momentum, your impulse was equal to 10 kilogram meters per second. So impulse is literally just the change in momentum. And there's a couple of different ways that you can calculate the change in an object's momentum. First and foremost is its mass times its change in velocity. If its velocity is changing, its momentum level must be changing, because you'd plug a different velocity into this formula and get a different momentum total, right? If something is speeding up, is it gaining or losing momentum? Gaining, not a trick, I promise. And slowing down, gaining or losing? Very good. So, note here, delta is always final minus initial. If you are gaining momentum, final will be bigger than your initial, therefore you get a positive answer. If you are losing momentum, your final would be smaller than the initial, so final minus initial gives you a negative answer. So a positive impulse means you gained momentum in a certain direction. A negative impulse means you lost momentum in that direction. And again, one of the easiest ways to describe that is just mass times change in velocity, because objects' masses don't tend to change spontaneously. But there is a second formula, well, I guess maybe a third or fourth, depending on how you read this formula out loud. There's another way to describe impulse, because there's another situation that causes impulse. The third, or I guess fourth part of this formula is force times time. What this tells us is that forces cause impulse. If you exert a force on something, you are trying to accelerate it to change its velocity, therefore you are changing the object's momentum level and causing an impulse. So forces cause impulses. And so really this one long equation here is kind of three equations lumped together, in my opinion. You've got impulse is defined as change in momentum. You've got impulse equals mass times change in velocity. And lastly, you've got impulse equals force times time. I just kind of ran all three together in my notes. All three of these describe change in momentum. They describe what an impulse is. This is the definition of impulse. This is what you can observe when something's momentum is changing. And this is why something's momentum is changing, because you exerted a force on it, causing its velocity to change. So all three of these are connected. That's why I set them all equal to each other. Again, in physics, we use math to describe the universe, and all three of these descriptions are just a different way of saying the same thing. So whichever one you might use in any given sort of a math question just kind of depends on what you know and what you're looking for. kind of like those four motion equations, which one you use depends on what you know and what you want out of them. So all of these describe impulse and change in momentum. Now, technically, impulse is a new variable, but it is just change in momentum, so it has all the same properties as the momentum variable. It's a vector, it's measured in the same unit, kilogram meters per second. But it just has its own variable because mathematicians and physicists decided that delta rho wasn't good enough, I guess. How does all this information feel for right now? Okay. Now, these are technically new formulas, so let's give them a little bit of practice. Anyone like baseball? Because as it turns out, the entirety of baseball, or at least the part involving the ball and the bat, is just momentum, impulse, and Newton's laws applied to sports. We are going to throw a baseball at Babe Ruth. Babe Ruth is going to, as a baseball player typically does, hit it with a baseball bat. And when the bat hits the ball, would you say that the ball's momentum changes? Yes, that is the entire premise of baseball. Ball has momentum this way, bat exerts force on ball, ball now has momentum that way. So by changing velocity, and definitely by changing direction, the ball's momentum will change, therefore the ball will undergo an impulse, and we are going to calculate that. So, to put some numbers to this feat of athleticism, we're going to throw a fast ball. This is the mass of the ball. That's, I believe, mass of a standard league issue baseball, 145 grams. And the fastball pitch in metric will be 44.7 meters per second. That's probably about 90 miles per hour. Babe Ruth is going to hit it with a baseball bat, and after being struck, the ball is going to turn around and be moving at 69.4 meters per second in the opposite direction. These are the metric numbers for something that Babe Ruth apparently actually did when those speeds are clocked, just converted from miles per hour to meters per second for simplicity's sake. I suppose then that return strike would be, that ball would be moving at like 140 miles per hour maybe, after he hit it. Baseball bats are very effective. And we are going to calculate the baseball's initial momentum, final momentum, impulse, and the force that the bat exerted upon the ball. Now, when doing math, I tend to find it useful to draw pictures. Especially if the situation at hand has distinct before versus after states. In this particular case, the before state, before the ball ever touches the bat, it is moving at this velocity forwards. So I'm labeling this as VI, initial velocity, 44.7 meters per second to the right. So this is our before state. The after state, after the ball and bat have totally collided, the ball's final velocity is 69.4 meters per second in the opposite direction after the bat exerts some amount of force on the ball. Note the direction change. That will be important. It's another reason why pictures are quite useful. This marker's running dry on me. So I'll just list all the variables again over here on the side. The mass of the ball, which won't change throughout this whole thing, 145 grams. Ball's initial velocity, 44.7 meters per second, excuse me, in one direction. The bat is going to hit the ball. Some amount of force is going to act on the ball for a time of 0.71 milliseconds. These sorts of things happen pretty quickly. And after that, the ball will turn around and move at 69.4 meters per second in the opposite direction. And we have a few things that we are going to solve for. But before that, any questions about the setup or the way that I've labeled these numbers? All right. So our first goal is to find the initial momentum and also separately the final momentum of this baseball. How do you think to go about finding the initial momentum level of the ball before the bat ever touches it?
Mass times velocity.
Mass times velocity. Now, if you're very specifically looking for the initial momentum, which I'm going to label here as rho I, rho initial, momentum initial, you'd want to make sure that you are using the initial velocity. Since the velocity is what's changing from before to after, you're looking for initial momentum, you want to make sure to use initial velocity. So I'm just going to be labeling those variables within my work here. I have not put an I on the mass because the mass is not changing. The mass of the baseball does not spontaneously become a different number. The only way that would really happen is if, I suppose it is possible in baseball for the skin to get knocked off the ball. That happens occasionally, right? But that's not happening in this case. I haven't said that that's happening. Mass does not spontaneously change. So, since it's not a vector and not changing, I'm just going to leave it as m and not mi. Now, do we want to use 154, I keep flipping those numbers around. Do we want to plug in 145 grams? Very good, we want to use kilograms. So how many kilograms is 145 grams? 0.145. Very good. There's 1,000 grams in a kilogram, so the kilogram number is 1,000 times smaller. Now, velocity is in the unit we want. Velocity is already in meters per second, so we're good to use the 44.7. And that will tell us the ball's initial momentum level. Does anyone's calculator disagree with approximately 6.48 momentum units? All right, so that is the initial momentum level of the ball. That is how much momentum the pitcher was able to put into it. And that momentum level is about to change, because again, the entire point of baseball is cause an impulse on the ball, change its momentum, either turn it around or, catch it. So really every part of the game is about impulse. So that's the initial momentum level. Now we also want the final momentum level. To do that, I'd advise using the same formula, but plug in the final velocity instead. The velocity changed from the initial 44.7 to 69.4. Note though that the ball turned around, so I am putting the opposite sign on that velocity vector. The ball turns around, velocity demands that we note the direction change. So I have plugged in negative 69.4 for that reason. Does anyone disagree with about negative 10 kilogram meters per second? All right. So we now have the initial momentum level. We now have the final momentum level. That's the first line completely addressed and answered. Any questions thus far? Next question then, given these two new pieces of information we have at our disposal, what is the ball's impulse? Given the numbers we already have, what do you feel like you'd want to do to try to calculate impulse, calculate J?
Impulse final minus impulse initial. No, momentum.
There we go, yes. Momentum final minus momentum initial. Very good, because this part here, the definition of momentum is, sorry, my bad. I basically did the reverse of what you said. The definition of impulse is change in momentum, and we know the initial and final momenta, so we can find the change in them. By the way, the plural of momentum is momenta, if I haven't mentioned that yet. I don't say it much, but it might happen occasionally. So, J equals delta rho, and remember from your mathematician brain, delta anything is change in that thing. Change in is always a final minus initial. So I've just rewritten J equals delta rho as J equals rho final minus rho initial. And that's exactly what we just found. We got rho initial, we got rho final. So now we can find that change. This is where the direction and the negative signs becomes important. Note, our final is a negative number. Our initial is a positive number. This happened because the ball turned around. The velocity was initially one way and changed directions. Momentum is a vector that inherits the velocity's direction. So the initial momentum points that way, the final momentum points that way. We have to keep those signs present when we plug our answers, our numbers into this. Final comes first. And so the first thing we write is negative 10.06. Final comes first, even if it's a negative number, and keep the negative. Then second comes minus initial. So we are then going to subtract and then write in the positive number that we found for the first part. So now we have a negative minus a positive. This is going to give us an even bigger negative, correct? Very good. So, what is that impulse going to be? I can do this in my head. negative 16.54. Does anyone disagree? Unit is still kilograms meters per second. The unit for impulse and momentum is the same thing. So that is the impulse of the ball, the change in momentum. This is a big enough impulse to take that initial forward momentum, get rid of it, and replace it with this much backwards momentum. So the fact that the impulse is negative tells you there's a lot of force, a lot of effort from the bat pointing that way to make sure the ball turns around. If these were both positive numbers, we'd get a much smaller answer, and we'd also get a positive answer. No, that's, never mind, rewind. That statement's not helpful. Note again that the direction is important, the negative signs here are important and mean something. We decided that negative points left, so this impulse points to the left because that's the direction that the bat is hitting the ball into. So, directions matter, the positives and negatives matter. How's that feel? Okay. So we've got the impulse of the ball. There's one more thing we're going to do with that piece of information. We're going to figure out the force that the bat applies to the ball. The force of Babe Ruth's swing arm. Now, there's a variable that was listed in the original description that we haven't used yet, and there's a part of the impulse formula we haven't used yet. Given what we currently have at our disposal, how should we go about calculating the force that the bat exerts on the ball?
To multiply that by the time,
Yeah, absolutely. Almost.
or divide that.
Very good, yes. The beginning and end of this long version of the impulse formula says impulse is equal to force times time. In order to cause impulse, you need to use force, because force is what causes acceleration and it causes change in velocity. So the force of the bat swing times the time the collision lasts, this is basically the time that the ball had to be able to accelerate, is also equal to the impulse. So if we know impulse and we know the time of the collision, we can find the force of the impact, the force that caused this impulse, this acceleration. So I'm just going to rewrite the formula as just this part. Impulse equals force times time. We've got the impulse part. We want force, and we just have to plug in the collision time. Now, all of our variables have a standard version of the unit that we like to use over any other variant of that unit. Do we want to plug in 0.71 milliseconds? Now, how many normal seconds is that?
0.00071.
Very good. Milli is 1,000 times smaller than base. So that's another 3 spots to point the decimal place to the left. As I said on Monday, this chapter is going to end up being about collisions. So this is kind of the first collision that we've examined here, because this is a collision between the bat and the ball. Things to note about collisions as we start doing collision type questions is that collisions always have a before state and an after state, which is why I drew this picture out like this, to kind of get in the habit of thinking about collisions in that way. Because this is literally everything you could ever consider to be a collision. There's always before crash, before forces are applied, and then after crash, after the forces have applied and everything is now settled into its new final velocity. And the thing to note about those collisions is they always take a certain amount of time. collisions are never technically instant. There's always a certain amount of time passing, and it's always a certain finite number. The longer a time a collision takes, usually the safer it is, but the less amount of time a collision takes, the more dangerous it tends to be. So the fact that this collision only lasts about this long, less than 1,000th of a second, means that, this is a very good swing of this baseball bat. The shorter a time a collision takes, the more dangerous it is. I'll show you the math for that in a minute. But all collisions take an amount of time, even if it's milli or nanoseconds. That's why if you, again, watched a lot of Mythbusters growing up. If you watch any freeze frame slow-mo video of, test crashes, basically, you can always see how many frames it takes for the actual crash to occur, for the crumple zone of a car to fully squish and the car to stop. That takes a certain number of frames, a certain number of finite seconds. So every collision has a before and after and takes time. We'll be exploring that this week and also in lab next week. But for right now, we're just going to calculate force. F is the only thing we have left, so we're just I'd recommend dividing both sides by time. Force is going to be equal to negative 16.54 divided by 0.00071. So what is the force output of Babe Ruth's baseball bat swing? Please let me know if your calculator disagrees with this, but I've got about 23,000 newtons. Which, for those of us who aren't used to the metric system, is about 5,000 pounds of impact force, which is, scientifically speaking, a lot. Now, as impressive as that number is, and as impressive as athletes are, I want to make it clear, Babe Ruth and similar athletes cannot deadlift that much weight. They could not lift up a 5,000-pound car with these same arms. That force output is with the assistance of a baseball bat. They could not punch with that strength, is what I'm saying. In a couple of weeks, we're going to talk about torque. The idea that applying a force at a radius kind of amplifies what you're doing, and that's why swinging a bat at the baseball is more effective than trying to punch it out of the air. Trust me, I did punch a few volleyballs in gym class. It didn't go well. It's better to use your arms as a swing arm. So, very impressive. But again, he cannot punch with this force output. That is not his muscles alone, that is with the assistance of a baseball bat. It turns out most sports are not only about impulse, they're also about torque and swing arms. Because most sports have something like a bat, or a racket, or a golf club, or something like that. I guess football and soccer. No, because in football and soccer you're still kicking things, and your legs are swing arms. Turns out all sports are about impulse and torque. But for the math thus far, any questions? How do we feel? All right. So, we found the impulse of the ball, found the force applied on the ball. Let's now relate this back to Newton's laws. This was the first collision that we have examined. The mathematical definition of a collision is when two objects exert force on each other for a certain amount of time. Those forces cause the objects in question to change velocity, therefore the objects both undergo an impulse. The momentum of both objects is going to change because of the force between the two of them. Some things to note about collisions. One, they always have a before state and an after state. Again, it's shown here. The before state is before the two things ever touch. The after state is, the 7.71 milliseconds after the collision happens. Their velocities have now fully changed, and they have exchanged as much momentum as they are going to exchange. So, what do the previous laws of motion we've discussed tell us about collisions? I first want to mention Newton's third law, as discussed on Monday. The third law, again, is the one that says action-reaction force. So if the bat hits the ball with this much force, that means the ball also hits the bat with this much force. Does that make sense? This is why baseball bats can get broken if you swing them hard enough. The ball literally will exert the same amount of force back, and if the bat can't handle it, it breaks. So, in this collision, the bat had the same amount of force acting on it, and that force was acting for the same amount of time. Those same 0.71 milliseconds that the bat acted on the ball also acted on the bat. So they exerted the same but opposite force on each other for the same amount of time. This means that the bat also underwent an impulse. A force acted on the bat for a certain amount of time, therefore the bat had an impulse. The bat's momentum changes along with the ball's. That's secretly what Newton's third law is about. Whenever one thing acts on another, there's an equal and opposite exchange of force, and therefore there will also be an equal and opposite exchange of momentum. If they're both undergoing the same force for the same amount of time, but the forces point in opposite directions, they will have equal but opposite impulses. Basically, the bat was able to give the ball this much negative momentum, just meaning leftward momentum, and in response, the ball gave the bat the same amount of rightward momentum. Because before the crash happened, the bat was moving to the left, right? Or rather, the bat was moving to the left, correct? After impact, the ball's pushing this way on the bat, and so the bat is going to slow down. The bat is receiving rightward momentum from the baseball. And that's why if you hit a ball with a bat, you feel it. You feel the bat slow down in that moment. Does that sound familiar? Same again is true for tennis or golf or any similar sort of sport. Frankly, again, even volleyball, because technically this is doing the same thing. It's just, you're not using another tool, you're just using your arms. So what Newton's third law is secretly about is that the objects that exert force on each other will not only have equal and opposite forces acting on them, but they will also have equal and opposite impulses. However much impulse momentum one object loses, the other must gain. I mentioned that momentum is this weird kind of invisible thing. Objects can possess it and they can also swap it. They can give it from one to the other. So again, the bat is basically giving a bunch of negative momentum to the ball, and in turn the ball is basically giving a bunch of rightward momentum to the bat. So, quick follow-up question. This is the same slide, but with one extra piece on the end. What is the bat's impulse, given everything we just discussed? Yep, positive 16.54. They exert equal but opposite forces on each other. So if a leftward pointing force was acting on the ball, giving it a leftward pointing impulse, a rightward force acts on the bat, and the bat would have an impulse of positive 16.54. And in turn, if I was to follow up with how much force does the ball exert on the bat, it would be positive 23,000 newtons. Again, just meaning rightward. This happens in every collision, all in a fraction of a second. So, insert your sport of choice. Couple details that I'd like to make sure are set in stone and in your notes before we break for the day and spend time looking at them on Friday. I've mentioned that Newton's law, I've hinted at this today. Newton's laws were secretly about momentum the whole time. We've been talking about them as if they're about force and motion, and they are. But because force and motion are also tied to momentum, that means that Newton's laws are also about momentum. This formula, one of the most common ones we've been using lately, net force equals mass times acceleration, is secretly a momentum formula. In fact, Newton didn't write it like this. Newton wrote it like this. That's what Newton put in his notes. But this is the same thing as this, and I can prove it. Force equals mass times acceleration. We know that acceleration is change in velocity over time. So I'm just going to take delta V over delta T and put it into this formula. I'm combining two formulas here. I know the two things that A is equal to. So I'm just going to write, instead of A, delta V over delta T. Sound fair? Same formula, just combining them. And we know from yesterday, well, from Monday and today, that mass times change in velocity is change in momentum. Therefore, Newton's second law, in addition to saying force equals mass times acceleration, also says net force equals change in momentum over change in time. And this is this. Delta rho is J, force is force, time is time. If I divided both sides by time, as we did here, that would be force equals impulse over time. Force equals impulse over time. Newton's laws have been about momentum from the beginning. It's all connected, this whole class. It's doubly why it's important for you to ask me questions when you're confused. Because if you didn't get this, now this won't make any sense. So please interrupt me if you're ever concerned or frustrated about anything. All this ties into what we're going to be doing on Friday and also in lab next week. The conservation of momentum. The idea that in a collision, momentum's not destroyed, it's just going to swap between objects. In the ball-bat collision, they just trade momentum back and forth. And we're going to prove how that works on Friday. Any questions? All right, let me know if you need anything. Have a wonderful day. Sorry.
We